between them, okay? Okay, so we can officially start. So good afternoon, everyone. My name is Fa, and I am a bachelor student. And as you may already heard, I've been working on the project for my bachelor thesis in the research group of Professor Marquez. And today I want to give you a brief insight on what I have done in the last few months. Well, the main aim of my thesis is to provide a method to calculate the correlation energy of the homogeneous electron gas in the 5-dimensional case. Now you might want to ask, why do we want to study the homogeneous electron gas? Well, because it is the simplest model in condensed matter physics. In this model, you just study a uniform gas of electrons that fills an infinite cube with positive ion background. And it is simple, but it is a really good theoretical description for alkali metals such as sodium, potassium, and cesium. As we all know, the atom of these elements have only one valence electron, and these valence electrons are weakly bound, and they are strongly delocalized, and therefore they can freely move in the lattice, and that's why the homogeneous electron gas is a really good description for this system. And here I have a cartoon of the homogeneous electron gas for you. The red dots are the electrons, and the yellow background represent the positive ion background. And although being considered simple, the homogeneous electron gas is a many-body problem, and that's why it is not a straightforward problem. Because as we all know, the problem of many interacting body problem has no analytical solution. Now let us take a look at the Hamiltonian of the homogeneous electron gas. It can basically be separated into three parts: the kinetic part of the kinetic energy of the electrons, the potential of the background, and the pairwise Coulomb interaction between the electrons. Now the first two parts, the kinetic part and the potential of the background, are no problem, but the pairwise Coulomb interaction is a headache. And one of the first methods to calculate the energy of the homogeneous electron gas is the Hartree-Fock approximation. And in this approximation, you calculate the energy of the system with the best theta determinant. And unfortunately, when you calculate the energy in this way, the energy that you obtain is higher than the actual energy of the ground state of the system. So that's why we define the correlation energy as the difference between the Hartree-Fock ground state energy and the exact ground state energy of the system. And one of the earliest attempts to calculate the correlation energy is the random phase approximation. But unfortunately, the random phase approximation has problem. And its problem is that it fails to take the short-range interaction between electrons into consideration. And that's why it is only valid for systems with high density, and therefore we need high-quality methods. And in 1968, Zingvi, Tosi, Land, and Schwellender proposed a new theory to calculate the correlation energy with greater accuracy, especially for systems at metallic density. Well, systems at metallic density are systems with the Wigner-Seitz radius Rs ranging from 2 to 6. And here I have taken directly the result from the paper of STLS, and you can see for system where the Rs from 2 to 6, well, for example, system with Rs equal to 3, the correlation energy calculated in the STLS theory is much smaller than the correlation energy calculated in the RPA. And since then, this theory was applied to a wide variety of research, and its sufficiency was proven for systems in lower dimensions such as 1D and 2D, and my friend Pascal will give us a closer look at this in his presentation. But for now, at this stage, I can say that these are the motivation for me to expand this theory to higher dimensions. Now, before we go into details, let me introduce you to some key feature of the STLS theory. Now, the STLS theory uses a self-consistent scheme to calculate the structure factor, and mathematically the structure factor can be defined as follows. is 1 over n, where this big N is the total number of particles multiplied with the expectation value of the density operator and its complex conjugate. And it is important to note that both operators are written in the reciprocal space, well, in the Fourier space. And physically, the structure factor would give you the scattering density when you investigate a material with X-ray scattering. One of the advantage of this theory is that it has low computational costs, as we will later see. All integrals needed for the calculation are one-dimensional. And another advantage is that this theory is inspired by classical theory. And there is one thing important I want to mention right now, is the usage of the dielectric function epsilon. And you may recognize this relation from your basic physics lecture. Well, this function epsilon connects the electrical field E with the dielectric displacement, the D field. Now let us look at detail and see how STLS actually did it. Before we start, let me remind you of your classical statistical mechanics class. When you want to study an ideal gas, you often take a look at the hierarchy of equation of motion in the phase space, and from there you will derive the Boltzmann equation to describe an ideal gas. And this is exactly what STLS did. They took the classical approach and considered the first equation in the hierarchy of equation of motion in the phase space. Now, in this equation, F is the one particle density, and it gives you the possibility to find one particle at time t at position r with momentum p, whereas F2 is the possibility to find two particles at time t, one located at position r with momentum p, and the other one at position r prime with momentum p prime. And the next equation in this hierarchy would be the dependence of F2 and F3. I'm sorry, I forgot to mention something. Phi of r minus r prime is the pairwise interaction between particles. And in our case, a homogeneous electron gas, this should be the pairwise Coulomb interaction between electrons. And the next equation in this hierarchy would be the dependence of F2 on F3, where F3 is the possibility to find three particles at time t. And this hierarchy is infinite. And to terminate the hierarchy, STLS applied this following ansatz. Now you may recognize the form of this ansatz. This is very similar to the famous molecular chaos ansatz that Boltzmann did to derive his Boltzmann equation. But and in this ansatz, you just say that the two particle density F2 is just the product of two other one particles density F. But STLS took a step further and included the pair correlation function. And this function is accounted for the short range interaction between electrons. And by making a really simple ansatz, STLS already included the short range interaction into their theory, which is one of the things that RPA fails to do. And when you apply this ansatz, you will obtain a partial differential equation. And by doing some really complicated math, at the end, you can solve the equation and arrive at this relation. Now this relation will describe the reaction of the system under a external perturbation. Now on the left-hand side, you have the induced charge density, which is the reaction of the system. And on the right-hand side, you will have delta V, which is the external potential perturbation. And this gigantic function right here connects the reaction of the system with the perturbation. And in this, and that's why it is the response function in the STLS theory. Now in this function, phi of q is the Fourier transformation of the Coulomb interaction. And chi 0 of q and omega is the response function of the free electron gas, well, electron gas with no Coulomb interaction. And right now you might wondering, why did I highlight this term in red? Well, because I want to make the comparison in the response function in the STLS theory and the RPA, and you can see that this term is what makes the difference. Now, mathematically, this term comes from the Fourier transformation of the product between the derivative of the Coulomb interaction with the pair correlation function that we included in the ansatz to terminate the hierarchy. And on the right-hand side, you can see up to a certain prefactor, E times Q, you have the Coulomb potential in the Q space. And this potential is corrected by the term 1 minus big G of Q, the term in red. And the whole thing sort of defined an effective potential. And that's why we can define the function big G of Q as the local field correction. And you can see that this is the direct result from the fact that we included the short-range interaction between electrons in the ansatz that I just shown in the previous slide. And in the RPA, you can see that the local field correction is 0. Well, when you put 0 right in here, then you will have 1, and you will obtain the response function in the RPA. And this collides exactly with the fact that the RPA fails to take the short-range interaction between electrons into consideration. And in the STLS theory, where we considered the short-range interaction, we arrive at a non-zero local field correction. Now, as I have mentioned before, the STLS theory will use a self-consistent scheme to calculate the Schottler factor. And now we shall take a look at the self-consistent calculation. Now, for practical usage, we will have to derive the local field correction and write it in this form, which is a gigantic d-dimensional integral. And it is important to notice that this integral, the d-dimensional integral, can be reduced to a one-dimensional integral by using the fact that the Schottler factor of a homogeneous system is only dependent on its factorial argument. And after that, you can use the spherical coordinate in the hyperspace to integrate out all the angle. And in the end, you will obtain a one-dimensional integral over the magnitude of Q prime. And using the response function that I have shown in the previous slide, you can derive the dielectric function in the STLS theory. Now, in this function, you may recognize the familiar function that I have mentioned before. Phi of Q is still the Coulomb potential in the Q space. Chi 0 is the response function of the free electron gas. And G of Q is the local field correction. And lastly, we will need a relation between the Schottler factor and the dielectric function. And this relation is derived from the quantum mechanical theory. And the scheme can be applied as follows. From the local field correction, you calculate the dielectric function. And from the dielectric function, you use this relation to calculate a new Schottler factor. And using this newly calculated Schottler factor, you can calculate a new local field correction and so on. But right now, maybe some of you have already recognized we are still missing something. Can anybody guess what we are missing? We are missing the first step because the loop has to start somewhere, right? We're missing the first iteration. And at this point, all of these functions are kind of unknown, actually, because we haven't gained any information about the structure of the material and how it will react under a perturbation. And that's why in the first step, we can make a very simple approximation, which is to use the Schottler factor calculated in the Hartree-Fock approximation. And we substitute the Schottler factor into this gigantic d-dimensional integral for the local field correction to obtain the local field correction in the first iteration, or I will call it as the local field correction in the Hartree-Fock approximation. And from there you can calculate the dielectric function epsilon and you can calculate the Schotter factor and so on. And we can repeat this calculation until we arrive at a desired convergence for the local field correction. Now we shall take a closer look at the first iteration. As I have already mentioned, you use the Schotter factor in the Hartree-Fock approximation, which takes the following form in the general D-dimensional case, where you have a 1 at the beginning, and it is subtracted by this double integral this double D-dimensional integral over 2 Fermi sphere, where QF is the Fermi wavelength, and the integral we will integrate over the Dirac delta distribution. And when we substitute this expression into the general expression for the local field correction, we will arrive at another monstrous gigantic double integral in the D-dimensional case. And the integral is also over 2 separated Fermi spheres. And Hubbard is actually one of the first to attempt to solve this integral by introducing this approximation. He just said that, okay, the absolute value of q plus k minus k prime to the d minus 1 power is approximate to q square plus qf square to the d minus 1 over 2. But this approximation is unfortunately only valid in the long wavelength limit, and unfortunately we can calculate this integral in the 3D case, 5D case, or even 2k plus 1 dimensional case. Now if you take a look at the integrand, you will see that up to a certain vector q, the integrand is only dependent on the difference k minus k prime, and this gives us the hint to make the substitution. We can call k minus k prime as a new variable, and I call it t. And because we are doing a double integral, we will need another variable, and the other one I will call it k plus k prime over 2. This substitution is actually inspired by the trick from the classical mechanics class that I took a few years ago. This is called the center of mass and relative coordinate trick. And there's a problem when we do this substitution. Well, in the old coordinate, we are integrating over 2 Fermi spheres. As you can remember, we are integrating over the region where k and k prime are smaller than qf. But in this new coordinate, we are actually integrating over the overlapping region of 2 Fermi spheres. And when you when you use the substitution, the volume of this overlapping region will come up in your integral. And fortunately, the volume of the overlapping region of 2 hypersphere was already calculated, and I just take this result to calculate and apply it and calculate the local field correction in the 3D case and the 5D case. And here I have plotted my analytical result in comparison with the Hubbard approximation. And as you can see, both functions show similar behavior in the long wavelength limit, and they both converge to 0.5. And using this function, you can calculate other function in the first iteration. Here I have the plot of the d-elliptic function in the 3D and 5D case, and because the function is a 2-variable function, I have plotted it over q and omega. And you can see, for example, the function epsilon in the 5D case and the 3D case, when plotted over omega, they have really similar form. Well, this curve right here is the real part of the d-elliptic function, and this term here, this curve right here, represents the imaginary part of the d-elliptic function. And in the end of the self-consistent calculation, you will obtain a new Schotter factor, and this Schotter factor can be used to calculate the interaction energy by using this formula. And in this formula, you still have phi of q is still the Coulomb interaction in the q space. S is obviously the Schotter factor, and omega should be the volume. And you might notice something. I have left out the term by Q equal to 0 because in the thermodynamic limit, this term where Q equal to 0 could cancel out with the potential of the background. And you can add this result for the interaction energy with the kinetic energy, and the kinetic energy is really easy to calculate, and you will have in the end the ground state energy in the STLS theory. And for the sake of convention, as condensed matter physicists really want to write everything in terms of the Wigner-Seitz radius, we can define a new quantity gamma, which is minus 1 over 2qf multiplied with the integral from 0 to infinity over SQ minus 1 to write, and then it is important to notice that QF, the Fermi wavelength, is the function of the Wigner-Seitz radius. And that's why we can call the quantity gamma a function of Rs. And using this, I have successfully written the general expression for the correlation energy in the d-dimensional case in my thesis. This is also important to notice that this is only valid for the case where d bigger than 1. In this expression, you can see the quantity gamma that we have just defined right here. This gigantic prefactor just comes from the fact that we have to do the integration in the hyperspherical coordinate. The second term is the exchange energy, and this is actually calculated by Robert Splessier, Dr. Benavides, and Professor Miguel Marquez for the project of Robert Splessier last year. Now, alpha d is just a constant that depends on the dimension, and epsilon 1 of C is the spin polarization, and it is 1 for unpolarized system. And to make sure that I have calculated everything correctly, I substitute d equal to 3 for an unpolarized system and obtain exactly the equation that was written in the paper of STLS. Now, as achievement, I can say that in this project, I have successfully understood the paper of STLS and reproduced the equation in the three-dimensional case, as well as expand the equation, fully expand every equation to the five-dimensional case. One of the open questions that remains is how to completely expand the theory to arbitrary dimension. The dimension is higher than 1. And in order to do that, I will have to find a method to evaluate the local field correction in the Hartree-Fock approximation, as well as calculate the real part of the response function of the free electron gas. In my thesis, I have successfully derived the imaginary part of chi0 for O dimension, but the real part is another gigantic d-dimensional integral. But we are hoping that we can actually solve the problem with the local field correction in the Hartree-Fock approximation and the real part of chi0 at the same time, because both integrals have really similar form, and that's why we can hope when we can solve one integral, then we can do another one really quickly. Another open question or another remaining challenge is to completely write the code to execute the self-consistent calculation. At this point of the presentation, I have successfully written the code for the first iteration, and now the remaining job would be to write the last part to do the calculation for a few more iterations. And when we have the code, then we're hoping that we can not just calculate the correlation energy and compare them with the RPA in the high dimensional case, but also investigate other physical properties of the homogeneous electron gas, such as the pair correlation function or the compressibility. And I have come to the end of my presentation. Before I officially end my presentation, I want to thank my friend Pascal for the helpful discussion when we try to understand the paper of STLS, and especially I want to give my most humble thanks to Dr. Carlos Benavides. Although being very busy with his work and he will have to take care of his newborn child, Carlos has spent a lot of time on Discord to help me and Pascal to finish this project. So thank you very much, Carlos. And now I can officially end my presentation, and I thank you very much for your attention.
We can have maybe some questions now.
Yeah.
Yeah. You want to start, Nikki?
So that's out, and we can ask other questions afterwards, or everything right now?
Maybe we will ask questions to Luke now, because then if we ask just at the end, then we have already forgotten what.
Then some stuff mixes up and then
yeah, maybe it's.
So most of this the question might be stupid.
No stupid questions.
Straightforward. So most of them I had on beforehand. You already answered. That's a good thing. So you introduced that within these STLS, everything is based on this equation of motion, right? So immediately when I saw this equation, it reminded me of the Boltzmann equation. You even said it in the talk, right? I haven't read it in the thesis, or maybe I haven't read it properly. So on the right-hand side,
it's the first equation.
Yeah, it's the first equation. I know, I saw the equation, but I haven't read the term Boltzmann.
Okay.
So when I saw it, I thought, that's the Boltzmann equation, right? So then I see this right-hand side term, where it said, so that's the pair interaction. So it's
you mean the phi of r minus r prime with the derivative.
Exactly, and then that's the two-particle occupation function, or let's call it like that in a dirty way. Is it possible to have another source term on the right, and not an interaction between electrons, but between other quasi-particles? Have you ever heard something like that? Because in the Boltzmann equation, it would be possible just to put another scattering term or an interaction term on the right-hand side. Between electrons and
unfortunately, I haven't heard of something like that because, well, to be honest, in my statistical mechanics class, I just took a look at the hierarchy of equation of motion with the collision term on the right-hand side, and I think in the framework of the quantum mechanical theory, maybe it can be possible to put another source term on the right-hand side, because in the quantum mechanical theory we can have this separation between the particle and the whole. Yeah. Then maybe we can do it, but I'm not really sure.
I don't know either.
But this term is actually just the collision term between particles.
Yeah. So maybe if I could say something about this. So I would sure think that one could add more terms, because this is the most basic starting point of the equation of motion. This is called the Boyer-Boff-Born green curve or something hierarchy, which we learned last semester in statistical mechanics. And the Boltzmann equation basically is, after some simplifications, follows from this hierarchy. So after this ansatz for the two-particle distribution function, and I think that's why one could always add a few more terms. Yeah. Because when it's possible in the Boltzmann equation,
particles will have more distribution.
Yeah, I think this should be possible because this hierarchy of equation of motion is actually derived from the Liouville equation. And in the Liouville equation, you just start with the Hamiltonian, and I think you can put as many terms as you want into the Hamiltonian. And this thing, I think you can exactly do it for the quantum mechanical theory, because in the quantum mechanical theory you have the von Neumann equation, which is the equivalent of the Liouville equation. So I think it should be possible.
Yeah. So maybe I think it would be possible to include like a linear combination of all possible particle distribution functions in this F2 or F1 maybe. So.
But in F1 it should be linear. In F2 it's a bit more complicated.
Because
you
one linear and
different kinds, right?
But it should be. I would think it should be possible.
Maybe that's a stupid question. I've written down on page 11, right? So you use this Hubbard approximation at a certain point to compare the both results. What can I read out of this approximation? So I haven't understood it really. So is it the elastic limit? So what's this Hubbard approximation you've written down for in layman's word.
Do you mean I should explain the approximation in words?
Yeah, this would be nice.
Yeah, I will have to think about it because what my initial thought when I see this approximation, I just see that okay, the term that this term, the place where this term show up is on the denominator, and this thing is actually the thing that causing the problem in evaluating the integral. So I think maybe to fully understand the approximation, you will have to try to extend the the absolute value of this vector right here, and see that if it's really collide with the q squared plus the Fermi wavelength to the squared, and see if they really collide. And when you do that, the denominator will become a constant because you are integrating over two vector k and k prime. And if this is a constant, then you can just pull it out of the double integral. And the other one should be the integration over the scalar product of q with k and q with k prime. And that can be done really easily.
In the physical motivations, you just, okay, you drop the k dependence. But what is it? Both, there are two spheres, right, that are interacting. I don't really get the physical meaning, but maybe that's no problem.
Isn't it that this is true, or let's say that the value of this integrand is more important when k minus k prime is close to k Fermi? Because if that is the case, that absolute value is the square root of k squared plus k minus k prime squared plus 2 times k, and then neglecting the angle.
Yes.
I think that would be the motivation. So
Yes.
when the momentum transfer is close to a Fermi momentum.
Okay, that
Makes
then
I guess.
totally. That's what I thought at the beginning. That's what I tried to say with inelastic and elastic. That's
Okay.
But honestly, I think you just looked at it and said, what can I do to this to get rid of this integral?
okay. That's fine. And both explanations are perfect. Right. That's it. We have something else. Blah blah blah. Blah blah blah. Maybe somebody else.
I have a lot of questions. Don't worry. I always have a lot of questions.
Maybe I will stop here and then afterwards.
Yeah.
Maybe I have some question in 5 minutes.
Yeah, don't worry. We can.
Don't worry, I will repeat some.
I have a lot of questions. I will not ask you everything.
Okay.
Don't worry. My wife always makes fun of me because
but also good for the audience.
For sure.
yeah, I always have a lot of things to ask. But let me ask you some things that are maybe not directly what you had in your slides, but kind of connected, but a little bit outside. So you mentioned several times the Hartree-Fock. That's your starting point, right?
Yeah.
I have two questions here about. So first of all, is it really important to use the initial structure factor coming from Hartree-Fock? Is it really important to use it, or can we just write down any structure factor and then from solving these equations you get to the same solution?
I think that should be possible, but in order to really examine to see that, I think we'll have to investigate the convergence behavior of other functions that we use in the self-consistent calculation.
Yeah, but there's nothing written in the papers. They always start from the Hartree-Fock, right?
They write they start with the Hartree-Fock approximation because it's this. They write, and I quote, "It's the simplest approximation one can make." That's
well. If it is the simplest approximation, I think that should.
Yeah,
be...
this is actually a very tricky question because you are solving effectively a nonlinear system of coupled differential integral equations, right?
Yeah.
No one tells you that the solution is unique to start with, right? You don't know. So it may depend on the starting point,
Yeah.
or not. There is also another tricky question that has to do with the representability, which is there any condition that the structure factor has to fulfill to be a structure factor, for example? But this is very complicated. It's just it's fine. Let's go back to the Hartree-Fock. Hartree-Fock has problems for the electron gas.
Yeah.
Do you know what problems it has? So if I do Hartree-Fock theory for the homogeneous electron gas, the result is not good.
Yeah.
Do you know why?
Well, I think that because in the Hartree-Fock you kind of neglect the pairwise correlation and approximate this whole potential with a single particle potential. It's kind of a fictive field.
Yeah, but there's something missing. So you are right. You use just the Coulomb interaction. And why is this so bad for an electron gas? Do you actually have the answer there? What do you neglect in Hartree-Fock? That's
Actually, I think this should be the local field correction, the short-range interaction between or maybe the interaction.
Even before. What do you neglect in Hartree-Fock that is so important for an electron or for a metal? It has to do with that epsilon over there. I'm sure you know, you're just not making the connection.
Yeah.
In Hartree-Fock, the interaction that you use is one over r minus r prime.
Yeah.
The question is this the physical interaction in a metal?
No, not actually. I don't think that's.
So what is physical? What should happen?
Physical should be a repulsion between electron because of the Coulomb interaction.
Yes, but I think you are going around with you're not seeing what I mean. There is screening, right?
Yeah.
Right. So the interaction in a metal or an electron gas shouldn't be one over r minus r prime.
Yeah.
Right.
Yeah.
It should be weaker. Would you agree?
Yeah, because you have the screening. Yeah.
Yeah, that's the problem. That's the physical origin of the problem.
Okay.
I'll just ask a couple of more things. Sorry. So we already discussed this. So what is the quantum mechanical counterpart of the distribution function of this f of r, p, and t that you have written there? Do you know what is the quantum mechanical counterpart or version?
I think that should be the density operator, the density matrix.
The density matrix, but it has to be it's of r and p. So how do we do? Our density matrix is of r prime. So do you know how to go from one to the other?
Should do the Fourier transformation to go from the R space to the Q space?
Yes, but there's one detail that is left. Yeah, you have rho of r prime,
yeah.
t if you want.
Yeah. And
you have to end up with a rho of r, of some r, and of a p. How so?
Can you repeat the question?
Maybe you just write down.
Yeah. Okay. So the question is, how do I go from?
You are right. So it's the density matrix.
Did the audience see that or not?
No, but yeah, it's okay. Anyway, the camera is flipped. I tried to fix it, but it's.
No, it's for me. It's on the right side.
For you, it's right. For me, it's flipped.
Okay.
Okay.
No, for me, it's right.
It's okay.
Okay. Yes, we have rho of r prime, and t, if you want.
Yeah.
So how do you go from there to a rho? So you need that r p. So how do you write this Fourier transform?
You mean how I go from here to from R to P and T?
The problem is not the t. Is what is that p that is what is that r and what is that p that is on the right hand side? Yeah, you have r prime on the left. You have an r and a p on the right.
Yeah.
So how do you go from one to the other? You're right. You have to do a Fourier transform, but what Fourier transform? It even has a name in physics. You know what it is? Well, I asked you, you have written it there. I mean, it's the center of mass and the relative coordinates that you have to use, right?
Yeah, but the only thing right now, if it's not the Fourier transformation, then
It is a Fourier transformation, but it's a special one. No?
So,
Yeah?
so I would say that I also don't know the name. We have not learned the special name.
No,
for
no,
the
not the
thing.
name, but can you write it down, the Fourier transform?
yeah, I think you should multiply it with the
Yeah, but what is IQ? I cannot see it from here.
a e to the power of p times r over the h bar.
Yeah, but what is that R that you put there? That is the question. What is it the first R that you have on the left?
No, actually, I don't think so, because if you're replacing the r prime with p, then this should be doing this Fourier transformation with r prime. To
Is it R prime? It's not R and it's not R prime. It should be the difference, R minus R prime,
yeah.
right?
And then and then
Yeah,
integrate
this
over
should be something like this, yeah.
over the difference or over one of
Yeah,
them.
you
No,
have to
over
change
the R
variables
minus-
into the center of mass
Yeah.
and relative coordinates like you had. And then you Fourier transform.
Okay.
And this is called the Wigner transform.
That's actually
It's
that's actually only something you learn in the masters, because I had it a few weeks ago.
It's possible, but I mean, you have these things in your talk. That's why I was asking. Maybe you knew. Last question that you have there is f of r and p, right?
Yeah.
So distribution function in statistics and very precise properties. It has to be non-negative and integrate to 1. This is probability distribution, right?
Yeah.
Is this true also for the quantum mechanical one? Do you know? I'm really going a little bit beyond. Don't worry. I know that you probably don't know these things. I'm just curious if you ever thought about these things. Yeah.
If you do the let me
Yeah.
That's the thing.
well, in the quantum mechanical case, then you have the density matrix, and once you do that,
Think about the two things separately. First of all, the normalization. Normalization means if I integrate, I get to 1. Do you think that is true also in the quantum mechanical case?
no, actually, in the quantum mechanical case, you should do the integration over the absolute value to the squared. So
No, of rho, of the distribution function. So it's
I'm mixing it with something else.
yeah, this is already distribution function. So do you think we get it's normalized?
Normalized should be,
Yeah.
Yeah. but if it can be also negative, I'm not sure.
yeah, it can be.
Yeah,
negative.
it can be negative, right?
It can be negative. And you can use it as a measure of entanglement
Okay.
because it's not a true distribution function. Okay. Sorry, but don't worry.
Yeah.
Go ahead. Let's do it the other way around. How do you think it went?
You first? Well, I think the presentation was okay, but the part where I had to answer some question, I really sucked.
Yeah.
So let's first ask your
Yeah, basically the same impression for me. So maybe you notice that normally I'm really outgoing, but when it comes to stuff like this, I have pretty much a big stage fright. So I tend to I think about what to say, and then basically in a few seconds I forget everything. So maybe you noticed on the first slide I basically improvised completely, and then at least I think
I
it got
noticed
better.
that you spent a little bit too much time in the first slide than I expected.
Yeah, that's because I completely. So and then I think personally it got better, and then I think the stuff on the slides regarding the thesis I explained well enough. Then again, like Dirk said, when it came to the questions, I'm not that proud about this part because, yeah.
We suck.
Okay, so let's ask a more objective question. Which grade do you think you're going to have?
Tough question.
Tough. Yeah. Want you first or me?
You don't have to answer.
I'm really bad at approximating
Yeah,
things like this.
So you're both going to have a 1.0. Now, can I give you my opinion? Our opinion. So our opinion is that your talks were extremely good. Okay.
Okay.
Have you seen other bachelor talks?
No.
You should do.
You should do.
Okay.
Okay. You were a bit more nervous than Duke giving the talk. That one could notice, but I mean that's.
I have also an explanation for that. Duke is way more rigorous in doing his work than I am. So I'm a lazy piece of work. I would say. I basically did the most part. So the thinking of what to say I did yesterday and structuring the thesis.
I think you can notice this difference between us.
Yeah.
He's really quick in reaction, where you put some question to his face, then his reaction is faster than me. I'm the other way around. I like to prepare things.
But he is way more thorough. He has the spirit to really dig into it, and I have problems with that. Since
You are certainly very different from each other. That's not the problem.
But we really like to work with each other because I think. Yeah.
So, but I think, well, we think, right, that the talks were really well prepared and
Thank you very
and
much.
really pedagogical, and it was a very difficult topic. Now, the questions, don't worry, because I do this just kind of to practice you from what the future can bring, because this is a very controlled environment, right? We're just us, and the only external, let's say, is Nikki, but he's not really very external, right? But when you go to a master thesis or a PhD thesis, then you have people that you have never seen in your life that will ask you questions, and I think it's better that you get used to this a bit more confrontational.
Yeah. It really showed that. Yeah. So the math in the thesis, in both theses, is really complicated. Yes. But I think math is just logic. So symbol does that, and we are basically to understand it. But to be able to understand the math, you don't need to really understand the physics. You just need to understand math. And I think your questions show that even though we did this stuff over the whole year,
we just caught up in the math, not on the physics.
We got caught up in the math, and we need to improve the physics side of it.
But that comes with time also. That comes with time, but many of the things that I asked are in Hardy's book in one way or another.
That's right.
So we went through them.
Yeah.
Right? But sometimes you are so much involved in the little details of the signs and the factors of 2 and whatever that you forget the
bigger picture,
the larger picture. But I mean, the things that you knew. I mean, you know how to do the Fourier transform.
Yeah.
You had it there.
Yeah.
Right. You had it there. But so don't worry about the questions. That was a little bit on purpose.
Yeah.
I do it. I don't do it to every student. I only do it to the students that are going to have 1.0. I'm not joking. Okay. So Discord is off, so they cannot hear it because Martin is going to have the master defense next week.